So there are two types of stretches. Let's jump in, and we'll come back to the formal definition in just a moment. Let's again consider f of x equals x squared. So we already know what it looks like. There it is. Something like that. You have to excuse my terrible drawing skills. Okay, so what would happen then if we put a number in front of it? So let's define something new. What would, say, 3f of x look like as a graph? Well, algebraically, it would be 3x squared. Nothing difficult about that at all. But every value of x has sort of tripled in height. It's got 3 times as big because the outcome, that y-axis, is 3 times as large. So a point that perhaps was here marked on the graph is now 3 times taller. So this is going to have the effect of stretching it with a scale factor of 3. Okay, the new graph, this is 3f of x, is there. The original graph is there. Look, everything has been stretched with a scale factor of 3. When we have a number that is inside the bracket, we can actually stretch it parallel to the x-axis rather than the y-axis. So what I mean by that is, well, okay, if we had f of 2x, what would that do to it? Well, now what would happen is if we draw, let's just redraw again, shall we? So here is my original f of x graph. Now what would happen is that the outcome that did happen for x will now happen half the distance across because it's doubled to get that value. So what I mean by that is, well, okay, if there was a point here that gave a certain outcome for x, now that outcome is there. And it's gone this way. It's half the distance. It's kind of been enlarged or stretched with a scale factor of 1 over 2. Okay, it's been reduced, it's pushed in towards that y-axis. So here's the summary, and this is hopefully making sense to you. If we have some factor that goes in front there, it has the reaction of stretching it vertically with that scale factor. Okay, scale factor, whatever that number is, p. And I think it's really interesting to make sure you understand that each point becomes p times its previous distance from the x-axis. We're talking about going up and down. Okay, now if we swap out x for qx, some number times x, then we're going to bring it closer to the y-axis. The scale factor enlargement is 1 over q, but it's going to get closer to the y-axis, okay? 1 over q times its previous distance from the y-axis. So we're talking about movement horizontally towards that y-axis. So let's have a look at some examples to make it a bit clearer, because it's not easy to explain this on a video. Okay, so here we have an f of x again, and we're going to draw y equals 3f of x to get started with. Okay, so let's use the orange pen for this one. This is part A. So we're saying every point is going to be stretched 3 times further away from the x-axis. So the origin will stay exactly where it is because it's on the x-axis. But that point that was at 2, 1 is now up there, look. Okay, and the point that was at minus 2, 2 is now going to be further down. I've run out of space, but it's going to be stretched 3 times further, somewhere down here. So what it's going to look like is that. Okay, let's swap out the pens. Let's go for the green, and we'll use that for part B. So f of 2x. Right, well, this one is where we bring them in twice as close to the y-axis, or enlarge its scale factor 1 over 2. So the original points are all going to move towards the y-axis. So the point that was at 4, 0, that is going to now be squashed in at 2, 0. And the point that was at 2, 3 is now going to be at 1, 3. Okay? Excuse me. I shouldn't say 2, 3, 2, 3. That was the one we already had. The point that was at 2, 1 is now going to go here, look, to 1, 1. So it's going to be squashed. The point at minus 4, 0 is now at minus 2, 0. The point that was at minus 2, 2 is now at minus 1, 2. So that green thing, and again, I'm going to have to apologize for my horrendous drawing skills, but that is what it's going to look like. It's going to get squashed in that direction in part B. Okay, so we'll do one more of these. Okay, this is a tricky one, but I want you to go through this with me. So we've got a function g of x, and that is what happens when the graph y equals 1 over x is transformed with a vertical stretch scale factor 2, followed by a translation of 3 minus 2. Can we write this expression in the form ax plus b over cx plus d? Well, we can certainly give it a go. Okay, so let's see what happens. First of all, a vertical stretch scale factor 2. So when we're talking about a vertical stretch, we're talking about up and down, aren't we? Right? Okay, so that means we're going to need to multiply this by 2. Now, I like to use a sort of little flow diagram for thinking about one of these combination of transformations questions. So let's do that now. So we start with 1 over x. The first thing is the vertical stretch. So that means we are going to be timesing by 2. And then we're going to do the translation, right? So when we've done the vertical stretch, we will have 2 over x. Right, now we're going to do our translation of 3 minus 2. So the 3 is going to mean that we replace the x with x minus 3. So 2 over x minus 3. Remember, that was the plan for those left and right movements. The minus 2 means we're moving down 2 places. Well, that means we just take off 2 off the end. So in essence, our g of x is going to be 2 over x minus 3 minus 2. Now, it's not looking quite right. It's not looking in the format we want it to be in. So let's try to create a same denominator for both and make this look a bit nicer. So we've got 2 over x minus 3 still, minus 2x minus 3 over x minus 3. I'm just writing that 2 in a way that has the same denominator. And now we can bring them together. Let's expand at the same time. So we'll have 2 minus 2x plus 6 all over x minus 3. So this is going to give us 8 minus 2x over x minus 3. Okay, are we in the correct form? Pretty much. Do you know what? I should have written the x's at the front, I guess. So our final answer can be g of x is equal to minus 2x plus 8 over x minus 3. Okay, there we are. Let's carry on, finish this question off. So find the asymptotes of y equals g of x. Okay, so yeah, we can do that. Now, we haven't covered this yet on these videos, but asymptote lines, we're going to have 2 types, the horizontal and vertical asymptote lines. So to find the horizontal ones, well, that's going to be a line which we can't cross. It doesn't have an x, it doesn't have an input. So what can't we input into this g of x? Well, we can't input 3 in, can we? Because we're not going to have a fraction with a denominator of 0. There's no outcome when that happens. So our asymptote is going to be 3. There's another one. The vertical asymptote is going to be found when we consider, well, what can't we get out of this function? What won't come out on that y-axis? Well, another way to think about it is, well, okay, if we imagine x is massive, positive or negative, doesn't really matter. If we imagine it's massive, what is going to end up happening? Are we going to be getting closer and closer to? Now, in both cases, the answer is y can't be -2. We're going to get closer to -2. It's not going to be a possible output for any value of x. How do I know that? Again, consider x being massive. Imagine x is, I don't know, 10,000. Our g of x will give us outcomes or an output that is that. Well, as we get bigger, 10,000, a million, these numbers on the end become more and more irrelevant. And actually, we'll end up sort of being able to cancel those and we'll just be left with the -2. So that's how I'm getting my second asymptote there. Okay, part C, sketch g of x. Okay, let's sketch it. So we can use those asymptote lines as a good reference point. I'm going to have to switch back to my favorite yellow pen. So x-axis, y-axis. We know that we've got an asymptote line here at x is equal to 3. Our second one was at y is -2, so we can draw that as well. Y equals -2. We know what 1 over x looks like. 1 over x looks like that. So we're just going to have stretched it and moved it. Very roughly, we're going to be looking at a graph that looks something like this.